All right, welcome to class, everybody. I hope you guys are having a good day today. So today's lesson is section 2.1, our first assignment in XYZ. So if you haven't gotten into XYZ homework yet and you're having any issues getting into it, please speak with me after class because that's kind of like top priority to get you guys into that so you can get started on your homework. So section 2.1 is about solutions to equations. And the actual homework questions should be pretty simple, I hope, for you guys. And a lot of you can probably finish them, even like without me teaching a lesson, because you've probably learned it in the past. So what I want to do with this lesson is to kind of show you guys the reason why we do some of the processes you guys are familiar with, and just kind of give some context and understanding around that. So the way that my lectures go is I will have like at the beginning of the lecture, we'll go through like kind of the why and like how to do the process. And then at the end of the lecture, I'll just start going through examples. And during that time, I'm totally fine if you guys want to work on your homework. So like if you want to bring your laptops and open them up and work on your homework during that example time, you're welcome to do that. Or if your learning style is better, just watching my examples and doing your homework on your own, you can also do that. And during that example time, I'm happy to go over any homework questions you guys have. You know, if you have any questions, I can help you with them. So the beginning part of class, though, I would ask that you guys are not on your laptops working on your homework, just so that like I don't get questions about something I already answered in the lecture. So at the beginning, we'll just explain the concepts and kind of give that foundational knowledge. This lesson is all about how to solve equations. And throughout this class, we'll learn how to solve other things like inequalities as well. But this class is about solving equations. So an equation is a math sentence or a math statement. So I want to kind of make an analogy to English. You know, so like in yesterday's class, we talked about how like math can be an art, or it's kind of like, you know, it can be thought of as an art. And algebra has a lot to do with, it's kind of like the grammar of mathematics. So like if we were comparing math to English, algebra would kind of be like taking a grammar class of like learning, well, how can I write math sentences? How can I rearrange them, but they still mean the same thing? So in English, as I'm sure you guys are familiar, every sentence has two parts. It has a subject and a predicate, right? So the subject is like what the sentence is talking about. The predicate contains a verb and describes what the subject is doing or what's happening to the subject. So as an example, if we had the English sentence, all the people in our class breathe air, all the people in our class would be the subject or what the sentence is talking about. Breathing air would be the predicate. And pretty much any sentence will always be able to be split up into these two parts. And math sentences have a similar type of structure. So the structure of a math sentence has three parts. So instead of having two parts like a subject and a predicate, a math sentence will always have two expressions, and then it will have a relationship between the expressions. So for example, you could have a really simple math statement like 2 + 3 = 5. In this statement, 2 + 3 is an expression and 5 is also an expression. And the relationship between these two expressions is that they're equal to each other. You could also have a relationship like less than. So you could say like 97 is less than 300. That's the relationship between these two expressions. And then you can also like add in variables with X's and things like that as well. So when we're thinking about math sentences, the goal of our class today is to find the solution to an equation. So a solution is the number that you could plug into the variable that would make the statement true. So technically we could make X equal anything. Like we could say, oh, X is 6. However, if we said X is 6 in this case, it would create a lie or a false statement because 2 + 6 does not equal 5. And so the goal of finding solutions is to find the value for X that will make the equation true. So this one's really easy. Everybody go ahead and call out, what would be the solution to this equation? 3, right? Because if I put in a 3 in for X, that makes the equation true. So what about this one? What would be a solution for this math statement? Okay, yep, because I could put in a 4, and if I put in a 4, I get 3 times 4, which equals 12, is greater than or equal to 12. So 12 is greater than or equal to 12. That's a true statement because they're equal. And so 4 would be a solution. So I'll write that down. Are there any other solutions? Yeah. Okay, anything greater than 4. I think I also heard somebody say 15. So let's use that as an example. If I do 3 times 15 is greater than or equal to 12. Well, 3 times 15 is 75. 75 is greater than or equal to 12. And so x equals 15 would be a solution. And like you said, pretty much any number bigger than 4 would be a solution, right? Like I could plug in a 5 or a 6 or a 7, like any of those numbers would make this math statement true. And so this math statement has an infinite number of solutions because I can plug in 4, 5, 6, 7, basically any number you can think of, as well as like all the decimals between them, right? Because I could plug in like 4.1, 4.2, 4.0012, like you could plug in an infinite number of numbers into this statement and it would make it true. So some math statements have an infinite number of solutions. So if we look at this equation, what would be a solution to this equation? Once you've got one, raise your hand and we'll test it out. Yeah. No solutions? Okay, so we have the hypothesis that maybe there isn't any solution to this. What do you think? Okay, if we try x equals 1, let's test it out and see if it makes the statement true. Because a solution will make, like you put it in for the variable to see if it makes it true. So if we do 8 times 1 equals 1 plus 7 times 1, that's going to be 8 equals 1 plus 7. And that is a true statement. So we at least have this as a solution. Yeah, what solution did you get? Yeah, so you're saying that I could choose any number, like any possible number, I could plug it in. So let's kind of test that out as a class. I mean, we don't have an infinite number of people in our class, but everybody go ahead and think of a number right now, plug it in for x, and let's see if that hypothesis is true. Out of all 40 of us, if you each choose some random number and plug it in, does it make the statement true? So I maybe might choose to plug in, I'm going to choose the number 4. So I'm going to plug it in and say, does 8 times 4 equal 4 plus 7 times 4? And that would be 32 equals 4 plus 28. So the one that I chose worked. Raise your hand if your number that you plugged in worked. Okay, awesome. So your hypothesis, I mean, we didn't prove that it's true because we didn't actually choose every single number that exists. But it does end up being true because this side of the equation could be simplified further. Because if I have a single x plus 7 x's, how many x's are on this side of the equation? 8 x's. So I could rewrite this equation as 8x equals 8x. Well, that statement, which is more simple than this one, that's always going to be true no matter what you plug in for x, because whatever number you choose for x, if you multiply it by 8, that is going to be equal to that same number multiplied by 8 because it's the same thing. So this would be an example or another example where it has an infinite solutions, and it's actually every single number. No matter what number you chose, if you plug it into this equation, it would make it true. So let's do another example. For this math statement, what would be the solutions that would be possible? Okay, why is it no solution?
Because if you minus x to the other side to get it, the variable by itself, it would cancel it out.
Okay, so you're kind of rewriting the equation by subtracting x from both sides, which would give us x minus x is 0 and 0 equals -2. Well, there's no way that that can be true. Like it's absolutely impossible for that equation to be true because 0 does not equal -2. And even if we didn't do this step and we just looked at this equation, we can see that this would not have any solutions, because if you choose any number, that number is not going to equal that same number minus 2, because subtracting the 2 will turn it into a different number. So this would be an example where we would have no solutions, because we end up with a false statement, regardless of what number you choose for X. So the way that we find solutions to equations is we kind of use the fact that when you have a math statement, if you add, subtract, multiply, or divide any number to both sides of the statement, it keeps the relationship the same. So for example, if we take like that really easy math statement, 3 + 2 = 5, if I were to add a number to both sides of the equation would still be equal. So my original statement was true, because 3 + 2 does equal 5. I could simplify it to say 5 = 5 if I wanted to. But if I add some random number to both sides, as long as I do it to both sides, it will still keep the statement being true. Versus if I only added something to one side, it would make a false statement, right? Because if I added 7 here, this part would simplify to be 12, and I would end up with 12 = 5, which is not true. But if I add it to both sides, then it makes like you get 12 = 12, which is a true statement. Okay, so I'm sure you guys are familiar with this. This is something that's covered a lot through middle school and high school. But basically we can add, subtract, multiply, divide, or we can also raise both sides to an exponent, or we can square root or cube root or do the root of both sides. All of those things will keep the relationship the same. And then we can also simplify individual expressions. So for example, if we started with this original blue equation, we could simplify one of the expressions, because remember, equations are written with 2 expressions and a relationship between them. So if I wanted to, I could simplify 3 + 2, which is 5, and I could write it as 5 = 5. And that still like makes the relationship stay the same. So those are the different things that we can use in order to help us solve equations. So let's say that we had a rather complicated equation like this one. So in this equation, we have the general structure of a math sentence. So we have an expression, another expression, and a relationship between them. So in order to find a solution to this equation, which isn't super easy to do in our head because it's rather complicated, we're going to simplify both sides and also use the fact that we can add and subtract, multiply and divide both sides of the equation by something. So let's start with simplifying, and I'm going to explain the concepts we use for simplifying on a different slide, and then we'll come back to this. So one of the things we can use to simplify expressions is we can use what's called the distributive property. So probably a lot of you guys know what this is. Can someone raise their hand and tell me what this would be equal to if we distributed the 2? Yeah. 6.
Sorry, never mind. I was thinking of the other one. But
Okay.
6x plus 10.
Perfect. Okay, awesome. And I'm assuming the way you got that was by doing 2 × 3x and 2 × 5, and that gave us those. So I talked a little bit, well, I can't remember if I talked to your class about this. Did we do the activity where you guys drew a cow yesterday? Okay, sorry, that was my other class then. But one of the things that I feel like really helps people understand math better is when you can see a picture that represents what the what the equation is actually saying. So I'm going to draw a picture of this because most likely you guys haven't seen why this actually works. So if I have 2 × 3x plus 5, the 2 is telling me that I'm doubling 3x plus 5. So I'm going to draw 2 groups, and that's basically representing the fact that I'm doubling. And then inside of my groups, I'm going to have 3 x's and 5 individual items. Okay, so that's kind of like the way that I'm representing 3x This is the 5, and then I have 2 times or a duplicate of those items. Is everybody good with how this picture represents this? Okay, now we're saying that this is equal to this. So if we were to draw a picture of this, we would have 6 X's and 10 individual items. So it would look kind of like that. So if you look at it, essentially what distributing is doing is it's taking it out of the groups. So we have 3 X's in each of the groups, and we have 2 groups. So 2 groups of 3 is a total of 6 X's. And 2 groups of 5 is a total of 10 things. Does that kind of make sense, how that distributed property works? So the idea is whenever you have something multiplied by things in parentheses, you take each of the terms that are inside of the parentheses, and you, like in this case, we would double each of them. If it was a 3, then you would like triple each of them. But whatever this number is that's multiplied by the entire set of parentheses, you multiply each thing in the parentheses by that. So that's one tool that we can use to simplify expressions. The other one we can use is combining like terms. So if I was to visualize this expression, the way I would visualize it is I'd say, okay, well, I have 12 X's. I probably should have chosen a number that was smaller, so I don't have to write as many. But I would have 12 X's, and then I'm subtracting 7. But whenever you see subtraction, you can also think about it as being 7 negatives. So you can either think about it as like taking away 7, or you can think about it as having like a debt of 7. So I'm going to use the color red to represent that. So I'm going to have 7 negatives, and then I'll have 5 X's and 9 positives and a negative X. So if you visualize it like this, it's easy to see how we could simplify this, right? Because if I have all of these individual objects, so I have 12 X's, 5 X's, and a negative X, well, I could just combine all of the X's together. Whoops. And if I have 12 X's plus 5 X's, that would be 17 X's. And this negative X is going to cancel out one of them. And so this would be 16X. Is everybody good with that? And then like with these objects, I could say, well, if I have 9 positives and 7 negatives, these 7 negatives are going to cancel out or neutralize 7 of the positives, which leaves me with 2 positives. And so this expression right here can be simplified to 16x plus 2. And sometimes you might have equations where you have like x's and y's, and you have like multiple letters, in which case you can combine like all the x's together and you can combine the y's together. So these are the 2 strategies that we'll use to help us simplify expressions. So we've got the distributed property, and then we've also got combining like terms. So going back to this equation, if we want to simplify this expression, on the left-hand side, I would notice that I have 2 sets of parentheses. So I'm going to distribute both of those. So let's start with this one. If I have 2 copies of 3x minus 9, then that means that 2 copies of 3x's is going to be a total of 6 x's. 2 copies of 9 negatives is going to be 18 negatives. And then on this one, if I have negative 5 copies, because technically this is subtracting 5 copies of 8x plus 1, but you can also think about it as negative 5 copies of 8x plus 1. And I think that's an easier way to look at it. So if I have negative 5 copies of 8x, that's going to be negative 40 x's. And if I have negative 5 copies of 1, that's going to be negative 5. And then that will be equal to the 7x minus 2 plus 5x. Is everybody good with that on how I simplified that? Now, these 2 sides of the equation can be simplified even further. So when I look at these 2 sides of the equation, I notice that I have 6 x's and 40 negative x's. So how many x's will I have on that left-hand side? Yep, negative 34 x's. And then how many whole numbers will I have? Negative what? 13? I think, is it
Negative 23.
23? Okay. Yeah, that sounds right. Okay, awesome. And then on this side, how many X's will I have? 12 X's. And then I also just have 2 negatives as well. So this is significantly simpler than our original equation, right? But it's still not super easy to see what the solutions are, because you've got like, oh, well, whatever my solution is, I'll need to do negative 34 times it, then subtract 23. And that has to be equal to 12 times that same number minus 2. So we want to continue solving this, but we can't do it by simplifying these expressions any further, because this expression can't be simplified and this one can't. So what we want to do at this point is ultimately we want to find out what X is. But in our equation, we have X's on both sides of the equation. So what we want to do is we want to get rid of one of the X's so that we only have a single X to solve for. And the way we do that is by canceling out one of the X's on either side. So I'm going to cancel out this one just because I like not having to work with negatives. But you could cancel out the 12X and you'd still get the same solution. So the way that you cancel it out is you add 34X to the left side. Because if you have 34 negative X's and then you add 34 positive X's, you're going to have 0 X's. So that will cancel it out over here. But remember, if I only add it to one side, that's going to make a false statement. Because, you know, like if you only add something to one side, it will imbalance the equation. So we're also going to add it to this side as well to make sure that the equation stays a true statement. Even though we don't know what X is yet, we want to make sure we keep it like the equation balanced as we're solving it. So when I do that, that's going to give me negative 23 equals, is that 46? 40X or 46X minus 2. Now at this point, what would our next step be? Yep, so we want to find out what X is. And so we're going to use our strategy of adding or multiplying or dividing something on both sides until X is all the way by itself. So because X is multiplied by a 46 and I'm subtracting a 2, like you said, we'll add 2 to both sides to cancel out the 2, which will help us get X by itself. So we get negative 21 equals 46X. Because on this side, negative 2 plus 2 is just going to be 0. So we're just left with the 46X. And on this side, negative 23 plus 2 is negative 21. And then what would our last step be to finish solving that? Yep, divide by 46. And I don't think that can be simplified at all. So I think our final solution would just be X equals negative 21 over 46. And you could take this answer and plug it back into the original equation. And assuming that we solved everything correctly, it should make the equation true. And I mean, in this case, I'm not going to do that because that's kind of a nasty looking fraction. I don't want to have to check that. But on your homework, your answers should tend to be whole numbers. And so I would recommend that you take whatever answer you get and plug it back into the equation to see if it really is a solution. So that's kind of the process of how we solve equations. So I want to do a quick little check-in. So on a scale of 1 to 5, how are you guys feeling about solving an equation like this? Okay, awesome, sweet. So on this part right here, do you guys ever have an issue with like not knowing which thing you undo first? You know, like whether you add a 2 or whether you divide by 46 first, because like the X is still, like the X kind of has these 2 things you have to get rid of. Do any of you guys ever have issues with knowing which one to do first? Okay, because so then I guess I don't have to teach this part that I was gonna say, but I'll just explain it really quickly. So when we created math, because like humans kind of developed math to describe patterns they notice, it kind of like builds on itself. So like when you first start learning math, you have addition, and then you learn that subtraction undoes addition, right? Then you have repeated addition becomes multiplication, and division undoes that repeated addition, which is multiplication. And then repeated multiplication becomes exponents, and exponents can be undone by doing roots. And so math is kind of built in like this pyramid structure where repeated addition becomes multiplication, repeated multiplication becomes exponents, and each one of them has something that undoes it. So the order of operations, which I'm sure you guys have learned about, oftentimes it's called PEMDAS. The order of operations basically says that you start off with grouping symbols. So if there's any parentheses, you have to do like that stuff first. And then you basically just go down the pyramid. So you simplify the hardest thing, which are exponents. Then you simplify the next hardest thing, which is multiplication and division. And then you simplify addition and subtraction. So this is order of operations. And when we're solving an equation, we basically go backwards of order of operations. Because if we knew what x was, order of operations would tell us that we have to multiply first and then do this subtraction. So when we're undoing this stuff to find out what x is, you basically work backwards. And you say, okay, I'm going to undo my subtraction, and then I'll undo my multiplication. So that's kind of the reason for why that works. Probably for most of you guys, you've already practiced it enough that it's just kind of automatic to know that you need to add the 7. But that's the reason why it works like that. It's because order of operations, you start at the hardest thing and work down. And when you're solving, you're basically undoing that or working backwards. So let's see. Do you guys feel ready to try an example on your own? Okay, awesome. Why don't you guys go ahead and try, let's do this one. So try this one on your own, and then we'll go through it together. All right. If you got the answer 5,000, go ahead and raise your hand so I can see. Nice, good job. So to kind of recap how we got that, we first simplified this left-hand side. So kind of going back to the sentence structure for math sentences, we had these two expressions and a relationship between them. So this expression can't really be simplified at all because it's just a single number. But this one can be simplified quite a bit by distributing the 0.10 to the stuff inside the parentheses, which gave us this. And then once the parentheses were gone, then we had 0.12 x's and negative 0.10 x's. So when we subtract that, we get 0.02 x's. And then the 1,500 couldn't be combined with anything. And then working backwards of order of operations, we undo addition or subtraction first. So we undid the plus 1,500 by subtracting 1,500. And then we undid the division by dividing by 0.02, which gave us this answer. And if we wanted to, we could take this number and plug it back into both of these x's. And it should, when you simplify all of that stuff, it should end up equaling 1,600. Because remember, the goal here is to find a solution which makes the equation true. So this number, if we plug it in for x's in the original equation, it should make the equation a true statement. So any questions on that? Yeah. At this point?
Oh, like at the very beginning, because I was taught like with those kind of equations,
Mm-hmm.
it makes things easier if you can multiply them to move the decimal point.
Mm-hmm.
So you don't have to deal with all that. That was before you have to use calculators.
Yeah. Yeah. So let me actually make a.
But I also got the wrong answer.
Yeah, let me see if I can do. Oh, no, I can't duplicate it. Okay, I'll just write it kind of small here. So like this. Okay, so what you're saying is like multiply both sides of the equation by, in this case, since we have two decimal places, you'd want to multiply by 100,
Yeah.
right, to get rid of those. So you can do this because this is multiplying both sides by the same thing. The thing that probably you made a mistake on is if you do 100 times this, that's just going to give you 12x. So you probably got that part. But essentially the structure of this expression is that you have two things that are being added together because this entire thing is a term. And so you would do 100 times this, and then you do 100 times this, and 100 times the 0.10 would give you just 10.
Oh, so you
And so you'd have 10 times this stuff, but you wouldn't multiply it by each one of these because the way that this is written right now, this is a single term because terms are things that are added or subtracted together. And this is just a really complicated term that has, you know, this times a complicated parenthesis expression. So if you did it that way, it would end up giving you the correct answer. Or another way you could do it is you could get rid of the parentheses by going to this point and then multiply everything by 100. Because at this point, now they're all separated out into individual terms and you don't have this like complicated term here. And so if you did it at this point, then it would work. Because I think that would give you like 2x equals 150,000, which equal, and this one would be 160,000. And you would end up with 5,000 once you went through and solved that. So you just want to do it after you get rid of the parentheses because these parentheses are kind of complicating the structure of how the expression is. Yeah, but that would totally work. And that's not a bad idea to do if you're trying to do it in your head. Because doing something like this is more difficult to do. But if you had 1,000 divided by 2, or no, actually it'd be 10,000 divided by 2, then that would give you the 5,000. Yeah, so good question. Any other questions on this? Okay. So let's see. Let's do one more example. So go ahead and try this one. All right, what did you guys get on this one? Raise your hand, yeah. Okay, so you simplified it by combining like terms, I'm assuming. So like you said, like on this side, so again, we've got two expressions and they're equal to each other. So on the left expression, if I have 4y minus 3y, that's going to give me 1y. And if I have 2 plus 5, that's going to give me 7. And then on this side, I get y plus 7 as well. So on this one, remember, we're trying to find solutions to the equation. So what would make this statement true? Is there anything that makes it true? Like, yeah, it will always be true because no matter what I choose for y plus 7 will always equal y plus 7. If you want to, like, if you kind of like going through like a procedure when you're solving equations, you can say like, oh, well, I have a y on both sides, so I need to get rid of the y on one of the sides. So I'll subtract y, which in this case ends up canceling out both of the y's, and you end up with 7 equals 7, which is always a true statement. And so that tells us that y can be anything. If you were to end up with something like 7 equals 2, you know, like if instead of this being, well, basically like if this side simplified to y plus 2 instead of y plus 7, that would be an example of when you'd have no solutions. So if you ever end up with like getting all of your variables canceled out when you try to subtract them or cancel them out on both sides, you look at what the result is. If it's a true statement, then anything is a solution. If it's a false statement, like 7 equals 2 or something like that, that means there's no solutions. And that kind of goes back to what we talked about at the very beginning of class when we did this problem, right? Like if you get rid of the x on both sides, you end up with a false statement, which means that there's no possible solution to this equation. Does that make sense? So you may sometimes get all solutions, like any number is a solution, and you may sometimes get no solutions depending on what the equation is. The last thing I want to go over is how to work with fractions. So if we look at this equation, we have the basic structure of any math sentence where we have these two expressions and they're equal to each other. So we can simplify these expressions by multiplying and distributing the numbers that are outside of the parentheses. So if I have 1/6 times 2x minus 3, I can distribute this out and do 1/6 times 2x as well as 1/6 times negative 3. So when I do 1/6 times 2x, I get 2x over 6. And when I do 1/6 times negative 3, I get negative 3 over 6. And technically these fractions can be reduced, but I'm just going to leave them as they are for right now. But they could be reduced if you wanted to. And then this is going to equal 7/12 times a negative 1/4 times x, which is negative x over 4, and negative 1/4 times 5, which is negative 5 over 4. Is everybody good with how I distributed those fractions? Okay, now at this point, if you were to follow the steps that we've learned so far, you would say like, oh, okay, well now I need to combine my terms. So you do 7/12 minus 5/4, which would be kind of hard to do because you'd have to get common denominators before you could add or in this case, subtract the fractions. So you'd have to find common denominators for these two fractions, combine the like terms, and then you would cancel out one of your x's. So I would probably cancel out this one because it's negative. So you'd like add x over 4 to this side, but then again, you'd have to get a common denominator between this and this. And basically all of those common denominators get really messy really fast, and it's really easy to make a mistake with it. So there's an easier way to solve fraction equations once you get it to this point where there's no parentheses. And the easier way to solve it is to multiply the entire equation by the number that would be a common denominator for all of the denominators. So in this case, we have a denominator of 6, 12, and 4. And what's a common denominator or the least common multiple for those three numbers? Yeah. Oh, perfect. Yep. So you could do 12. So we're going to multiply the entire equation by 12. And the reason why we're doing this is because multiplying by the least common multiple, which is like the number we use as the common denominator, it's going to cancel out all of the denominators of the fractions, which means we won't have fractions to work with anymore, which will be much easier to solve. So the way that we multiply 12 by a fraction, so let's do that first one where we have 12 times 2x over 6. What we have here is we have some multiplication, and then we also have some division. And because the multiplication and division are on like the same level of the math pyramid, where like, you know how like it goes addition, subtraction, then multiplication, division, and exponents, because they're on the same level of the math pyramid, you can do them in whichever order you want to do. You could do multiplication first, or you could do the division first. So if you multiplied, you could go 12 times 2x, which would give you 24x, and then divide by 6, which would be 4x. So that's one way you could solve it. The way I prefer to do it, though, is to do 12 divided by 6, which is 2x. So I'll write this out again. So I would do 12 divided by 6, which is 2. And then I do 2 times the 2x, which also equals 4x. So you can see you get the same answer regardless of whether you multiply first or whether you divide first. I prefer doing the division because you end up with smaller numbers. You know, because like in this case, it's not that bad to do 24x divided by 6. But if like this was a big number, like say like a 15, you do like 12 times 15, and then you'd have to like calculate in your calculator what that is and then divide by 6. It would be a lot easier if you just did 12 divided by 6 is 2 and then did 2 times 15. Does that make sense? So you can do it either way, whichever way makes the most sense to you, but I'm going to do it by dividing first because I like working with small numbers. So if we look at this first one, 12 divided by 6 is 2 times 2x is going to give us 4x. Then 12 divided by 6 is 2 times negative 3 is going to give us negative 6. Is everybody good with how I'm doing that? Now I'll do the same thing on this side. So 12 divided by 12 is 1 times 7 gives me 7. And then 12 divided by 4 is 3. And 3 times negative x is negative 3x. Then 12 divided by 4 is 3 times negative 5 is negative 15. And as you can see, this equation is way simpler than this one in terms of solving, because now we don't have any fractions and now we can just solve and figure out what x is. So I'm going to do this by simplifying the left-hand side, or sorry, the right-hand side of the equation. So I'll do 7 minus 15 is negative, is it 8? Okay, so we get 4x minus 6 equals negative 3x minus 8. And now we have two x's on, or like we have x's on both sides of the expression. And I want to ultimately find out what x is. So I'm going to get rid of one of them. Which one would you guys prefer to get rid of? The negative 3? Okay, yeah, that's the one I would get rid of as well, just because I don't like working with negatives. But you could get rid of the 4x and you'd still end up with the same answer in the end. So I'll add 3 x's to both sides to get rid of the x on that one side. And that gives me 7x minus 6 equals negative 8. And then from here, I just undo order of operations. So if I knew what x was, I would multiply by 7 and subtract 6. So to undo that, I work backwards. Yeah. Okay. Okay. So to undo this, I'm going to work backwards and add 6 to both sides, which gives me 7x equals negative 2. And then I ran out of room, but if I divide both sides by 7, I'm going to get x equals negative 2/7 as my answer. And that would be my solution for this equation. And if I took that fraction and plugged it back into the original equation, it should make the original equation true. So that's how you deal with fractions. Do you guys have any questions on that? Okay. So similar to what you asked about with the decimals, make sure you do this step of multiplying by the common denominator after you've already simplified the parentheses. Because if you were to multiply by a common denominator like before this step, I mean, technically you could do it. It's just kind of complicated to think about it because this original expression has two terms, but this term is a rather complicated one. And same thing here, like this entire thing is a single term. So if you were to multiply by the common denominators at this point, you would multiply this by 12, which would just give you 2 times the parentheses stuff. And then you multiply this by 12 and you multiply this. But it's a lot easier to think about if you expand it and distribute it first. So if you have parentheses, always distribute them as kind of your first step. And then you can get rid of the parentheses or get rid of the fractions from there. Or in the decimal case, you could get rid of the decimals. Yeah. So you're saying like reduce these? Like write this as x over 3 and this would be like 1/2? Is that what you're saying? Yeah, so you could totally do that. You would still actually end up with 4x minus 6 at this point. So I don't do it just because it's adding in like an extra step that isn't necessary. Because I'll solve that over here. So like you're saying if we wrote it as like x over 3 minus 1/2, when we multiply that by 12, you get 12 divided by 3, which is 4, times x is going to give you 4x. 12 divided by 2 is 6, times -1 will still give you the -6. So you'll still end up with this, but reducing your fraction just gives you like an extra step. So you can do it. I just don't do it because it adds in an extra step. Yeah, good question. Any other questions? Okay, cool. So we have like 3 more minutes. So if you guys want to look through your homework and see if you have any questions that you'd like help with, go ahead and do that. I'm happy to answer questions. Usually it won't take this long, by the way, for me to go through the instruction part. Usually it'll be about half and half, but today there's just like a lot of explanation part.